Okay, so this is a very common question, and it brings in circular motion and resolving forces, stuff we did last year. So what do you got? We've got a ball of mass 0.25 kilograms attached to a string that is rotating with a speed v along the horizontal circle of radius r equals 0.33. So you can see that it's kind of circling in this direction, tied to a piece of string on the ceiling. Now the first question is to draw and label the arrows to represent the forces on the ball. So in effect you are drawing a free body diagram for the forces on the ball. So on the ball we have the weight down. It's moving in a circular path, and remember, if something's moving in a circular path, there is a force there. And of course the string is pulling up. Now this really illustrates the need for thinking about the ball only, because if we consider only the ball, then the string is pulling up. Okay, so we have three forces acting in these directions: T, F and W. It then goes on to ask you if the ball is in equilibrium. Now, as you know, when something's moving in a circular path, there is always a force acting towards the centre. And if there's a force, then there must be an acceleration. Now, if something is in equilibrium, there would be zero resultant force. And a zero resultant force would mean that you'd have constant V or zero V. And that's definitely not having. We have an acceleration and we have a force towards the centre. So this is definitely not in equilibrium. The third question asks you to work out V. Now, the easiest way is to look at the data, and as you can see from the data, we have an M and we have R. Okay, so it's nice to make this kind of notation when you're reading the question, because it will allow you to start thinking about what relationships to use. The appropriate relationship would be this one, mv squared over r, because that's what you're given. 2 pi r over t would not be useful as we don't have the period. So where do we get started with this? Well, in order to use this formula, I should say F, in order to use this relationship, we really need to find the value of this force. And for that, we're going to have to use a little bit of the trigonometry that we used last year. We're going to resolve forces. Now, the first thing is that vertically, it is in equilibrium. The ball isn't moving up and down. Okay, the ball is moving along this plane. So we can safely say that the forces up balance the forces down. So if we resolve vertically, if you remember from last year, you can see that T, or the component of T in the vertical direction, is going to be equal to the weight. Now the component of T, if we have a look at this arrangement, you've got 30 degrees there, so you must have 30 degrees here. So the component of T in this direction would be T cosine 30. Okay, so that's our vertical, T cosine 30, and that's equal to the weight down, which is the mass 0.25 times 9.81. From here you can rearrange to find T easily. T should give you 2.83 newtons. So now we have the value of T. Now why do we need T? Because we need to find F. As you should be able to tell, F is due to a certain component of T in the horizontal direction. So if you can work out how much of T is acting horizontally, then you've got F. Now T, let's have a look, if that's 30, that would be 60. If we resolve horizontally, T cosine 60 would be equal to f. And that f would be equal to mv squared over r. So if we put all of those values in, okay, so 2.83 times cosine 60, the mass is 0.25 and the radius is 0.33. So if we rearrange and solve for the speed, we should get 1.4 meters per second.